Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. You're being hit by trillions of invisible particles every second and you never even notice. If I told you right now, as you're watching this, trillions of ghosts are passing straight through your body every second. Yeah, pause for a second. Don't click away just yet. These things come from the sun, from deep space, even from exploding stars. Sounds like the start of a horror movie, right? Relax. No jump scares here, and you definitely don't need to call the police. Here's the twist: these things are almost impossible to catch. They have no electric charge, their mass is so tiny it's basically negligible. They pass through Earth like you walk through air. Put simply, they're the universe's most wanted escape artists. You try to catch them, they ignore you. You try to chase them, they walk through walls and disappear. So the real question is, how did humans ever manage to detect them? And here's where it gets even crazier: the person who did it didn't go to space. Didn't build a giant particle collider. He did something far more absurd. He went into a mountain, dug out a massive underground space, and then filled it with water. And after that? He waited. Not a day, not a year, but decades. That man was Masatoshi Koshiba. And today, we're diving into a story that goes against everything you think you know about genius. Because this isn't a story about raw talent or sudden breakthroughs. It's about patience, stubbornness, and what happens when someone just refuses to stop. As the saying goes, slow and steady wins the race. Let's rewind. 1926, Japan. No spotlight. No dramatic origin story. Masatoshi Koshiba was born into an ordinary family, and I mean really ordinary. Not the kind of kid you'd pick as the main character in a movie. He wasn't a prodigy. No solving equations at age 3 kind of story. More like, teachers comment, not bad. Which, let's be honest, is just a polite way of saying gets the job done. Nothing special. If life were a video game, his starting stats would be average. And the timing, not great either. He grew up during wartime. Resources were scarce, the environment was tense, even getting a stable education wasn't guaranteed. You'd expect a dramatic turning point here, right? A sudden awakening. A moment where everything clicks. Nope. He stayed the same. Slow, unremarkable, almost forgettable. But something subtle started to change. High school. One teacher. Every great story has one of these key NPC. This teacher didn't give motivational speeches. Didn't say, "You're destined for greatness." He just did one simple thing. He showed him physics. Not formulas, not memorization, but questions. Why does light travel the way it does? Why do objects move? Why is the universe the way it is? And something clicked, quietly. For the first time, Koshiba realized the questions were more interesting than the answers. He didn't suddenly become brilliant. No cheat codes unlocked. But he started thinking a little longer than everyone else. Others finished homework and left. He stayed a bit longer. Others said, "I get it." He asked, "Do I really?" It was a tiny change, almost invisible. But like a seed, it started to grow. He still wasn't top of the class, still not the teacher's pride and joy. Honestly, if you were in his class back then, you probably wouldn't remember him. But one thing became clear. He wasn't fast. But he never stopped. Others sprinted. He ran a marathon. Rain or shine. No audience. No applause. Just running. At the time, it didn't seem useful. Exams don't give extra points for persistence. The world doesn't hand out rewards just because you try hard. But years later, that effort cashes in. Because some people don't win at the starting line. They win because they never leave the race. And that habit, of not stopping, it would eventually lead him to do something almost no one else was willing to do. Something that sounds, frankly, ridiculous. Sitting in a mountain watching a tank of water, waiting for a signal that might never come. The war ends. The world doesn't hit a restart button, but Japan does enter something like a forced reboot. Cities rebuilding, the economy recovering. Science? Basically loading from a corrupted save file. Not enough labs, not enough equipment, definitely not enough funding. In short, everything important was missing. You'd think that would slow science down. But here's the funny thing. When resources go down, one thing goes up. Questions. Big ones. Not how do I solve this problem, but how does the universe even work? Sounds ambitious, right? No equipment, and you're asking about the cosmos. But that's how it goes. When you have nothing, you start asking what actually matters? Koshiba kept moving forward in this environment. Eventually, he got into the University of Tokyo, one of Japan's closest things to a knowledge hub at the time. But even there, resources were tight. Imagine trying to cook a Michelin-star meal with a dull knife and a single hot plate. What do? Most people complain or lower their expectations. But there's another type of person. They change the question. Given what I have, what's the most important thing I can do? That's the direction Koshiba started heading. He stopped focusing on what he lacked, and started asking what is worth my time. Sounds simple, but it's not, because most people let conditions define their ambition. Bad conditions lower the goal. He flipped it. If it's already this hard, I might as well do something truly difficult. That mindset? It quietly shapes a lifetime. No resources, but space to think. No equipment, but time to choose a direction. And that choice changes everything. Soon, an opportunity appeared. Not in Japan, but across the ocean. The United States. If Japan's science at the time was a system just booting up, the US was a fully loaded server. Koshiba decided to go. He arrived at the University of Rochester. For most people, studying abroad is just that, studying. For him, it was like plugging directly into the global research network. High-speed connection, no lag. Here, he encountered particle physics for real. At its core, it asks a simple question. What is the smallest building block of reality? But follow that question far enough, and it becomes, what are the fundamental rules of the universe? Now he was surrounded by people with resources, with cutting-edge equipment, with access to the latest ideas. The lab wasn't barely usable anymore. It was, if you can imagine it, we probably have it. The impact? Massive. Like upgrading from an old phone to the latest flagship overnight. Not just faster, a completely different world. He moved from the edge of the network to its core. Ideas moved faster, collisions of thought sparked new research. One casual conversation could lead to something groundbreaking. But here's where things get interesting. Most people follow the trend. Hot topics, quick results, papers, recognition. Koshiba? He started drifting towards something else. Something almost no one wanted to touch. Why? Too hard, too slow, too uncertain. The field was called Neutrinos. Even the name sounds like trouble. They barely interact with anything. You can't see them, you can barely detect them. Studying them is like waiting in the dark for a cat that doesn't make a sound, and also can walk through walls. You can't catch it. You're not even sure it's there. But Koshiba saw something different. Where others saw difficulty, he saw, if we do catch it, what changes? That's the fork in the road. One path is crowded, the other is lonely. One gives quick rewards, the other might give nothing for decades. He chose the second. No applause. No one calling it a smart move. Honestly, it looked irrational. But here's the thing. Some problems are important because no one is willing to wait for them. And as another saying goes, good things come to those who wait. Koshiba didn't just wait. He committed to it. Here's where things take a turn, a slightly unhinged one. Most scientists, when choosing a research topic, look at two things: how hard is it, and is it worth it? Masatoshi Koshiba looked at a third question: is anyone willing to wait for it? And the thing he locked onto? Neutrinos. Now, the name sounds harmless, like a background character. But what they do, that's a whole different story. If I had to sum it up, neutrinos are the most antisocial particles in the universe. No electric charge, mass so tiny it's almost a rounding error, they barely interact with anything. You reach out to grab one, it ignores you. You build a detector, it pretends it doesn't exist. Studying neutrinos is basically like trying to catch a shadow in the air. And that shadow, it doesn't want to be found. Here's the wild part. They're everywhere. The sun is constantly producing them. The explosions across the universe are flooding space with them. They pass through Earth like a tidal wave, through your body, through everything. And yet, you feel absolutely nothing. It's like standing under a waterfall and not getting wet. Sounds impossible. But it's real. So the challenge isn't no signal. It's that the signal is too indifferent. Almost every neutrino just passes straight through. No trace. No interaction. Only a tiny fraction, a ridiculously tiny fraction, will interact. Once for a split second, then it's gone. Your job. Out of billions of nothing happen moments, catch that one moment where something did. How hard is that? Imagine standing in a thunderstorm, trying to hear a pin drop, and you don't even know when the pin will fall. Most people would say, yeah, I'm out. But Koshiba didn't walk away. He didn't switch to an easier problem. Didn't pivot to something more practical. He made a call. Go for the hardest one. Because he realized something. If you can catch a neutrino, you're not just running an experiment. You're talking directly to the universe. As they say, nothing ventured, nothing gained. Alright. So the problem is set. Now comes the real question. How do you even do this? You can't just shout into the void, hey neutrino, come here. It won't answer. So you need a detector. A system that can catch an event that almost never happens. And here's the catch, you can't build it in a normal lab. Too much noise. Cosmic rays, environmental interference, false signals everywhere. You'd never know what's real. So what's the solution? It sounds crazy. Go underground, deep underground. Eventually, he chose a place, the Kamioka mine. And no, this wasn't a fancy research facility. It was a mine. Most scientists work in labs. Koshiba, he said, let's dig a cavern inside a mountain. And not a small one. We're talking about a space big enough to hold a building. Then came the next step. Fill it with water. A lot of water. Not a tank, not a pool. An enormous volume of ultra-pure water. This setup would later be known as Kamiokonda detector. The idea sounds simple, but it's beautifully precise. Very occasionally a neutrino will collide with a particle in the water. When that happens, it produces a tiny flash of light. Extremely brief, extremely faint. Your job. Catch that flash. So they lined the walls with light sensors, like a group of night watchmen staring into the dark, waiting for a single blink. Sounds poetic. In reality, it was brutal. The water had to be perfectly pure, the instruments had to be incredibly stable, the environment had to be silent. Any impurity, any interference, and the signal disappears. And the hardest part? You don't know how long you'll wait. Could be the next second, could be years. So this wasn't really an experiment. It was a vigil. He wasn't waiting for data. Or papers. He was waiting for a knock. A faint, almost impossible knock from the universe itself. Then came 1987. No warning. No announcement. But the universe did something extraordinary. In a distant region known as SN 1987A, a star exploded. Not just any explosion. This was a supernova, the final act of a star's life. The energy released? In a single moment, it can outshine an entire galaxy. Sounds spectacular. But here's the catch. People on Earth didn't see anything yet. Because light takes time. That supernova is about 160,000 light-years away. So the light, still traveling. But the universe has a habit. Sometimes, it sends a message first. And that message isn't light. It's neutrinos. When a star's core collapses, it releases a burst of neutrinos instantly. And these particles, they don't get blocked. Not by dust, not by gas. They just go a straight line. No detours. So the outcome is kind of amazing. The light is still on its way. But the neutrinos? They've already arrived. It's like the universe sent a text. Something just happened. Details, still loading. Meanwhile, deep inside that mountain in Japan, the water is still there, the detectors are still watching, and Masatoshi Koshiba is still waiting. No one knows if anything will happen, or when. And then, it happens. February 1987. Inside the detector, something triggers. Not just one event. A series. A cluster of signals within a short time window. Faint, but clean. Like hearing a few clear knocks in a completely silent room. What's the first reaction? Excitement? No. Suspicion. Is the equipment malfunctioning? Is this noise? Did something break? They check everything again and again. Same result. The signals are real. And the timing? Perfect. At almost the same moment, other detectors around the world picked up similar signals. That's when it hits. This isn't coincidence. This isn't error. This is a cosmic event. Hours later, the light finally arrives. Astronomers look up toward the large Magellanic Cloud, and they see it. The supernova. Everything lines up. First came the neutrinos, then came the light. No mistake. It's like getting a message, "I'm here." And hours later, the person walks in. Turns out, the universe gives a heads up. So how big was this discovery? One sentence. For the first time, humans understood the universe without relying on light. Before this, astronomy was all about seeing. Telescopes, light. But light has limits. It gets blocked, absorbed, distorted. Some places, light can't escape at all. Like the core of a star or the heart of an explosion. They've always been black boxes. But neutrinos? They don't care. They pass straight through. They carry raw, untouched information from the very core. Which means, we're no longer just seeing the surface. We're listening to the inside. Like a doctor who doesn't just look at a patient but hears the heartbeat. And what Koshiba did? He built a stethoscope for the universe. That tank of water, those decades of waiting, all of it, paid off in just a few seconds. The data? Only a handful of events. A dozen or so neutrinos. Sounds small. But in this field? That's a flood. Because you're dealing with something that almost never speaks. And on that day, it did. Quietly, but clearly. From that moment on, astronomy had a new language. Not just light, but neutrinos. And the universe? It stopped being something we only observe. It became something we could finally hear. After that moment, everything shifted. Not in the sense of one more paper published. Not another scientific achievement unlocked. Something deeper happened. Humanity gained a new way to sense the universe. Because before this, we didn't really understand the universe, we just looked at it. Telescopes pointed at the sky, collecting light, analyzing it. Red, blue, bright, dim. It was like watching a silent movie. Beautiful visuals, .0 sound. Then neutrinos changed the game. Now there was another option. Not just seeing, but listening. Listening to what? To the information that light could never carry. The inside of stars, the core of explosions, or regions buried under layers of matter. Places where light can't escape. But neutrinos? They slip through. Like an insider walking out of a locked room, carrying the message no one else could deliver. That's how neutrino astronomy was born. If that sounds abstract, think of it this way. Before, you could only see the outside of a house. Now, you can hear the conversations happening inside. That's not an upgrade. That's a whole new dimension. And it all started with one thing: a tank of water and decades of patience. Masatoshi Koshiba didn't make neutrinos easier to catch. What he did was more important. He made it possible for humanity to notice them. But the story doesn't stop there. Because once you open one door, you can't help but wonder what's behind the next. So the project grew. If the first detector was impressive, the next one was on another level. The Super Kamiokanda. Think of it as everything turned up to 11. Bigger, deeper, more sensitive. If the original setup was a room, this was an underground ocean. More water, more detectors, higher precision. It's like switching from cheap earbuds to top-tier studio headphones. Suddenly, details you never knew existed are crystal clear. And this time, they weren't just waiting. They started studying neutrinos. Their numbers, their direction, their energy. Piece by piece, they began mapping an invisible world. And then something strange appeared. Neutrinos seemed to change. At first, that sounds wrong. A particle is a particle, right? But neutrinos come in different flavors. And as they travel, they can transform into each other. It's almost surreal. Like leaving one city, and halfway through the journey you become someone else. Keep going like nothing happened. At first, people didn't buy it. But data doesn't lie. And over time, the evidence from Super Kamiokanda became undeniable. Neutrinos oscillate. That's what we call it, neutrino oscillation. And here's why that matters. It means neutrinos have mass. Tiny, yes, but not zero. And that one detail? It shakes the foundations of particle physics. Because for a long time, they were assumed to be massless. Change that assumption and the entire framework needs updating. Not a small fix. A rewrite of the rules. Funny, isn't it? A particle that barely exists ends up rewriting how we understand existence itself. There's something poetic about that. Looking back, that original choice still seems irrational. Slow, difficult, uncertain. But it gave humanity something unprecedented. A new way to touch the universe. Koshiba didn't make things easier. He just did one quiet thing. He made the inaudible audible. Now let's bring it back to you. You're sitting there. Maybe scrolling, maybe zoning out. Feels like nothing is happening. But here's the truth. Right now trillions of particles just pass through you. No warning, no trace. They move through your body like wine through a curtain. You didn't feel a thing. This isn't science fiction. This is reality. These ghosts are neutrinos. They come from the sun, from deep space, from stars that exploded long before you were born. Some of them started their journey before you even existed. They traveled across the universe only to pass through you in an instant. Sounds wild. But what's even wilder? It happens all the time. You don't need to do anything, they just keep coming. In absurd numbers. If they made a sound, you'd probably go insane from the noise. But here's the catch. You can't hear them. For thousands of years, humanity has looked at the universe. We watched light, tracked motion, recorded change. But an entire layer of information was always there, completely ignored. Not because it wasn't important, but because we couldn't sense it. Until Koshiba put that tank of water inside a mountain, and everything began to change. The discovery of neutrinos was just one more particle. It changed how we observe reality. Before, we were like photographers, capturing images with light. Now, we're also like doctors. We can listen. Light tells you what's happening on the surface, neutrinos tell you what's happening inside. Two completely different stories. Like looking at a building. It might look perfect outside, but you have no idea what's going on inside. Neutrinos? They bring you information straight from the structure within. Suddenly, things that were invisible became accessible. The core of the sun, the heart of a supernova. Once black boxes. Now, partially open. And here's the surprising part. This kind of pure science doesn't stay isolated. It spills over. To detect such tiny signals, scientists had to push technology to the extreme. We're talking about sensitivity so high it's like seeing a match light in complete darkness from miles away. That kind of tech? It doesn't stay in the lab. It shows up in medicine, environmental monitoring, or radiation detection, even data science. Because when signals are raring, noise is everywhere, you learn something powerful. How to find patterns in chaos. Sound familiar? That's basically how financial models work, how AI systems learn, even how your phone decides what videos to show you. From noise, find the signal. Same game, different scale. But the biggest impact? Not technology. Perspective. You start to realize something. The universe was never far away. It's not just out there in the sky, not just inside telescopes. It's right here. Around you or through you. You just couldn't hear it before. It's like standing by the ocean without hearing. You see the waves move, but you don't know they make sound. Neutrinos are that sound. Soft or faint, almost non-existent. But always there. And what Koshiba did? He didn't create the universe. He didn't change neutrinos. He simply helped us realize. We've been standing inside a vast, silent storm this entire time. And slowly, you begin to notice. What changed wasn't just science. It was how we think. Science used to feel like a puzzle. Clues given, answers found. Now, the questions themselves are changing. It's no longer just what's the answer. It's are we even asking the right question? Because sometimes being stuck isn't about intelligence. It's about direction. Koshiba didn't optimize old methods. He didn't just make telescopes better. He changed the approach. If light can't show it, maybe we shouldn't rely only on light. Sounds simple, but it's not, because it means admitting the old way has limits, and having the courage to do something that looks slow, even foolish, like waiting decades inside a mountain. As the saying goes, Rome wasn't built in a day. That mindset quietly influenced a generation. In Japan's physics community, you start to see a pattern. Not rushed, not flashy, but deep. From Shinichiro to Monagatō Masatoshi Koshiba, there's a common thread. They weren't always the fastest, but their questions? Fundamental. Tamanaga reshaped how we understand interactions in quantum electrodynamics. Koshiba? He taught humanity how to listen to the universe. Sounds poetic, but it's real, because the true power of science isn't giving answers. It's showing you out here are better questions to ask. So here we are. Neutrinos are still hard to catch, still elusive, still ignoring us most of the time. They didn't become easier. We just became better. Not stronger, but smarter. Not faster, but more patient. Now pause for a second. Right here. Right now. Trillions of neutrinos just passed through you again. They're still invisible. That hasn't changed. But something else has. Humanity now knows they're there. And more importantly, we've learned how to listen. So next time you feel like you're putting in effort and getting nothing back, remember this. There was once a man sitting in a mountain, staring at a tank of water for decades. No applause. No guarantees, not even certainty it would work. And then one day, the universe knocked. Very gently. And he heard it. The universe doesn't explain itself. It's quiet, almost indifferent. But every now and then, someone spends a lifetime just to make it speak. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.